Okay, everyone, welcome to the 2134 crash course. Hope everyone's excited. I, Anuka, and Leith are going to be presenting today. Sorry for the late start, and let's just get into it. Leith, do you want to start?
Sure. We'll do attendance afterwards.
Yeah, we'll do attendance at the end.
Okay. Mr. Camera. Hi.
You might want to move closer so you can see the blackboard.
Yeah, that's right. Alright, hi everyone. I'm Leith, and I'll be doing the first two topics of the crash course. So that'll be transformers, so it's the end part of magnetically coupled, and then I'll be doing a bit of transient. So that's both first order and second order. So if you guys have any questions, make sure to voice them. But without further ado, I guess we just get started. So, just got a bit of slides here, and they've got some theory. So if you can remember back to maybe it was like week 7 when you did, it was actually week 5 that you did transformers. We got a bit of theory here about how they work. Naturally, they're magnetically coupled circuits, and so we relate the input voltage to output voltage, and they're related by the turn ratio. So if the ratio is greater than 1, it's a step-up transformer, so the output voltage is greater than the input voltage, and then the opposite's true when you've got a step-down transformer, so our N is less than 1. And current has the inverse property, so your input current for a step-up transformer would be greater in the input than the output. And so if it's a step-down transformer, then your current would increase as you go through the output, from the input to the output. All right, and here's some diagrams from the textbook, I believe, about some of the dot conventions. So the way they work is that there's different polarities you've got that are assigned for the currents and the voltages depending on where the dot is. So what you can see is that as a general rule of thumb, if you want to find what the polarities are, I think I've got it here. Yep. So if the input voltage and the output voltage are defined to be positive or negative at the same dotted terminals, so be more specific, to give an example. If you look at the top left, you can see that the positive terminal of V1, V2 on the top, and they both correspond to the dot. Therefore, the voltage ratio is positive. For current, it's a bit different. The way that it works is that you want the currents, if they both enter the same terminal, or they both enter the dotted terminal, then their ratio is negative. And so if one enters a dotted terminal and another one leaves it, then it becomes positive. Right, and here's the last thing about reflected load before we go into a question. So reflected load is just sort of creating an equivalent circuit for your magnetically coupled circuits, or your transformers more specifically. And the way it works is that you take your load resistance and then you can sort of project it onto one circuit. And so the advantage of this is that it makes circuit analysis a whole lot easier. It just becomes one mesh essentially. And so it just makes analyzing the circuit really, really convenient. Naturally, if you didn't want to use this, you'd have to use the properties that we went through earlier. So you'd have to use the input and output voltages and the input and output currents. And then you could do nodal mesh or any sort of circuit analysis algorithm in order to find whatever you're trying to find. Are there any questions about the theory before I go into the first question? No? How do I check this stream? Just need to see if there's questions online. That'll be alright. Actually, I'll just go through the question. There won't be anything left. Alright. So here's example 1. This was from a past paper. I think it was maybe 23T1. And so the question asks, for the ideal transformer circuit shown below, so figure 1, they've given us a bunch of values for all of these different, they've given us values for all these like quantities and the capacitance and the resistance. And they've given us the frequency that the circuit's operating at. And so the first part asks us to find the complex power supplied by the source. Or redraw the circuit here. So I've got a, well, that doesn't feel nice, but you're right. So we're given that the source is 120 volts. And then the impedance, so they've given us the capacitor and the resistor, but we can combine them into one impedance because we're given the frequency that we're operating at. So I'll have to use my calculator real quickly. So this will be 2 times 2 pi. So what I've pretty much done here is that I'm trying to find, oh, that's not good. Use this one instead. Find Z here, and so Z, can you guys see that? Yep, alright, that's good. Z will be equal to 1 on J omega C, and I'm going to factor in the resistance as well. So that Rp is 4. We know what C is. C they've given us as 442 microfarads. And then omega is going to be 2 pi, or it'll be 2 pi times 60. Times 442, let's call it micro, times 4. And so just plug that into my calculator. What we would get is that is not times 4, that's plus 4. There we go. 7.2, 1 angle minus 56.3 degrees. Just save that. Right, so that's Z. And then what we've got is that we've got that load resistance, but we don't want to work with that. We want to find the complex power supplied by the source. So this circuit would be so much easier if we can make it into one equivalent circuit. So what we can do is that we'll reflect the load into the left mesh, and so we'll get one circuit, and then we can use, we can simplify the resistors or the impedances, and then we can get the current through it, and then we'll get the complex power from that. So I'll just do that. So we know that RL, actually let me just rewrite this. So we'll call this R for reflected. And we know that reflected R, based on the equation that I've got here. So the reflected impedance, or resistance that we're working with, is going to be the load resistance divided by n squared, or the ratio squared. So this is going to be R, if I go back to the question, it will be RL. So RL is 75. Divided by n, and n is 5, because that's the ratio between essentially the left mesh and the right mesh. You think about it that way. And so that'll be 5 squared, 75 on 25, that's 3. That's 3 ohms. So this is 3. And so what we could do is that we can simplify these two together, and then we'll get one equivalent impedance, and then we've got this input voltage. We'll do I is equal to V on Z to find I, and then we can find the power through this by using P is equal to V times I conjugate. Now, one thing to keep in mind is that when we were given V, they said it was an RMS, so we don't have to divide it by half. All right, so let's just do that. So I'll take Z, so I find with that angle, degrees. Great, I just call that amps, sure. All right, and so what we can do is that we can take this, and we can take this is an RMS, probably should have written that down, multiply them together, and then we'll get the complex power from the voltage source. So we would get P is equal to 120 times the conjugate of this. So this would be 13.01 angle would make that negative 40.6. Oh, there we are. Instead of that, if I just whack that into my calculator, what we would get is that we get 13.01. Where is it? Minus 40.6. Okay. So this is 1561.2 angle minus 40.6 degrees. All right, any questions about that first part? I think it's fairly straightforward. All right, let me just rub out some of this so that I've got more room. I will keep some of the important values though. So I'll just rewrite them here. So we know that Z, actually no, let's write them a bit. Z is equal to 7.21 angle minus 56.3 degrees. Great, so I can get rid of all this junk. I don't need this anymore. Great, so that's the first part. Right. So the next part, or it's actually still the first part, but it's the second part of the first part, is that when you find the average power absorbed by RL. Okay, so if we want to find the average power through RL, what you'd have to do, generally speaking, is that you'd get the input current, and then you would multiply it by the ratio, or you'd take into account the ratio. So what we know is that the terminals are on opposite sides. The first mesh, we are going out of the dotted terminal. This one we're going out of the dotted terminal. So what that means is that we'll have I think it's negative. It would be a positive, so it would be a positive ratio. So you'd get I2 would be equal to I1 times by negative. We know that this is a step-up transformer, so the current goes down by a factor of 1 on 5. And so you'd find the current I2, and then you multiply it by RL, but then you have to actually you don't have to unreflect it. You just have RL, and then you multiply it that way. I'm going to do it a bit differently. So what we can say is that when earlier I said that these two circuits are equivalent, the reflected circuit and that circuit over there. So what that tells us is that if we want to find the power through RL, that's the same as finding the power through this, because it came from that. I just reflected it in. So what that says is that instead of doing the conversion to find I2, all I have to do is just take into account or just use the power from this and the current that we've got. So what I can say is that the power is going to be equal to, we're working with RMS currents. This is just the resistance here. So what we can say is that this is going to be I, this will be the absolute value of that squared, times R, which is 3. Yeah. And so I is just that. So if I put that into my calculator, I'll square it, times 3. There we are. 57 watts. Are there any questions about that, or how I got? No? All right. Awesome. Where's the rubber? Where did I put it? They're right here. Yeah, it's right here. No, I didn't even see it. Okay, that was the first part. Second one. Find the value of the resistive load RL required to have maximum average power transfer to it. What is the maximum average power on the load? All right, so this is sort of mixing the first topic that we had with this topic. Now, if I wanted to analyze this circuit as is, and find the maximum average power transfer, I'd have to use Thevenin. I mean, I'll still use Thevenin, but it makes it really awkward because we've got this thing in the middle, and that doesn't really play nice. So what I can do is that, like what I've done here, I can use Thevenin, but for this circuit, it's a lot more straightforward because what we know, right, is that it's already been simplified for us. This is an equivalent circuit. I can call this, we won't call it 3, we'll call it just R. Actually, no, we'll call it something else. You know, RR. RR is still fine, but that's no longer 3 because we want to find RL given RR, if that makes sense. So what we can say is that if I want to get maximum power through this, right, which is the same as the maximum power through RL, this, the resistance here, has to be equal to the absolute value of Z. If you think back to topic 1, it says absolute value of Z, which is equal to 7.21. That's the value through that. So that will be the second part. That will be the second part. That's not actually the second part. That's RR. Now, in order to find RL, we have to use the inverse of this property that we used then. So ZL, or it's actually RL, is going to be equal to n squared times our RR, which we found is 7.21. We know n is 5, so this is 25 times 7.21, which I think is around like 180. Let me check. 25 times 7.21. Yeah, 180. We'll just call it 180. So that's RL. That's the RL we need in order to maximize the average power. Okay. And so it asks us also to find the maximum average power on the load. So that is exactly the same situation as we had before. So I could get the current and then go to the second mesh, but I don't actually have to do that because I know the power through this is the same as the power on the right mesh. So what I'll say is that I want to find the power through there. What I know is that P max, I can just steal, actually no, I can't steal the formula from the formula sheet because that only works for complex loads. This is a real load. So the way that we would do this is that it's still essentially very similar. So what we do is that we've got this and we've got that. So we'd add them together and we'd divide it by this. So we get 120 divided by, actually, that's not what I want to say. This is I RMS of this new circuit. Let's call this I RMS. And this is 120 on 7.21 angle minus 56.3 plus 7.21. You guys kind of see how I did that? So I've just taken this and I've taken this, so it's this part of the circuit, and I've divided V on Z to get I. And so if I plug that into my calculator, what I'd get is 120, up to that, it's 150, well, that's 56.3 plus 7.21. And then let's just make that a bit neater. Okay, so that's going to be 9.44 angle, doesn't matter actually, because what we do is that we want to find the power through there. That's P times absolute value of I squared times R. We found R at 7.21. And so that would just be this. We take this and put that in there. And so we put that in. What we'd get is that we get 9.44 squared times 7.21. And that's our answer. That's 642.5 watts. Yeah. And that actually makes sense. So if you can maybe do a bit of a sanity check, you'll see that this power is larger than the power that we got for the previous the load resistance that we found. So this is the optimum. All right, are there any questions about that part? If not, I'll just finish the last one real quick because I think that's fairly simple. So all it asks is that it's just like a word answer problem. It just says, is the ideal transformer step up or step down? We know the ratio is 5, so it's 1 to 5. So therefore it's a step up. And the second part is, why are these transformers used? So one explanation you could give is that we know that when we have transmission lines, big, long transmission lines, we want to maximize the voltage and we want to minimize the current. And the reason why we want to minimize current is that you just sort of give it by this equation. So P loss is equal to the current squared times R. This is assuming that you've got resistive power lines, right? And so what happens is that you want to minimize this I in order to mitigate your losses. And so as a result, you're maximizing your voltage. Any questions about that? No? All right. Next question. I broke this one in half as well. That's fine. I'll just use it. Okay. So this question we're given, it's another transformer question, but this one's a bit awkward. And the reason for that is that usually we'd like to do reflections, right? But what we've got here is that we've got a connection from the first mesh to the second one directly. And so we can't use your standard reflected load. We actually have to do this from sort of like first principles, essentially. So what we can do is that we have to find V. So V is the voltage across the 5 ohm resistor. And we just have to analyze the circuit, essentially. We know we've got an AC signal. So what we can do is that we can do AC analysis. We'll use phases. And so the capacitor will turn into an impedance, and the resistance stay the same. And we can choose to do either nodal or mesh. I think I'll go with nodal. I'll go with mesh. Mesh is nicer. And I'll explain why in a sec. So let me just draw out this circuit. So our source is for cosine of 3t. In the frequency domain, we would get for angle 0. And this is at omega is equal to 3. And so what we get is that if I draw the circuit again, I'll draw it in terms of impedances. So this is going to be our source. This is, we'll just call it 4. We can ignore the angle. This is 1. And then we've got the capacitor coming up. Now the value of the capacitor is 1 on j omega c. We know our our omega is 3. And we know the value of our capacitor is 1 on 3. Oh, so it's just 1 on, or just minus j. This is minus j, this value. This comes around there. This part comes through here. This is 2 ohms. So this doesn't get too messy. Okay. And this comes down. This comes down. Great. And then this becomes our output resistor. This is 5. Okay. And then this comes around here. All right. Great. So that's our circuit. We need to find this. V of t. We need to find it in time domain. But we'll switch it to the time domain at the end. So what we can do is that we start annotating our voltages. So we know that this is V of t. This is V, or we'll just call this V actually. because we're working with phases. So this is V. This is also V, because it's connected directly. Now this is related to this by our transformer. So what we can say, if I'm using mesh analysis, we've got one mesh current coming through here. Something wrong?
Oh no, I'm just fixing something.
Oh, okay. Yeah. So I'll call this I1, this is I2, and up here is I3. Yep. Can you guys still see that? I feel like it's going down slowly. There we are. Okay. And so what we can say is that the current here is coming down through the dotted terminal. The current's going up here, out of the dotted terminal. They're opposites, so therefore it's not negative, it's positive. So our ratio between I1 and I2 is a positive times the ratio, which is 4. So what we can say is that I2 is equal to 1/4 of I1. And then our voltages, these are both positive. We've defined them to be positive because we want to. And then we can say that this voltage here, this one, is going to be, this is positive, so the ratio is positive. And so this input would be just 1/4 of V. Can you guys see how I've kind of done that? So this times 4 would give us this, and the reason for that is because of the turn ratio, accounting for the negatives and the positives, which there are none, thankfully. All right. Now, what I can do in order to make this, I'll draw that over there, so just so it's less messy, is that I can make this a bit easier to analyze by getting rid of some of the variables that we don't care about. So I1 is already related to I2, so I can just get rid of I1. We know that I1 is just going to be 4 times I2. And then we can just start doing our mesh analysis from now. I think we've got all the information we need. So we'll do mesh at 1. So mesh at 1. What you can see is that it goes up -4, and then it does, it's 1, the resistance is 1 times, that's not 4, that's 2. Oh, actually, no, it is 4. Never mind, that's 4. 4I2, go in there, and then through here we've got plus 2 times the difference in currents. We're doing 4I2 minus I3. And then from there, so we've got 4I2 minus I3, and then we come down here. We've already got it in terms of V, so we'll just leave that there. So that's plus 1 on 4 V, because that's positive. We define that to be positive. And that's equal to 0. Now, for the second mesh, there's not much information we can kind of extract from it, because we know that this is V, and this is V. So if we did KVL, we'll just get V is equal to V. So it's not really that useful. What we can find though is that V is equal to I2 times 5. So what I'll just say is that from the second mesh, useful information we can extract is that V is equal to 5 I2. Right. And then from the third one, this one's a bit awkward to look at, but we'll start from there and then we'll come around here. We'll go in between the transformer, and then we'll come out here. So what we can do is that this is going to be minus J times, so that's the impedance, times I3. And then from there, then we've got plus V minus 1 on 4V. So it's plus V minus 1 on 4V. And then it's going to be plus 2, and then we're going this way, so we're doing I3 minus 4I2. And that's equal to 0. All right. now I've got the equations, I can just get rid of this circuit. We don't need it anymore. It's kind of useless. That's all the information we need, and I'll show why in a second. I just need a bit more space. That should be enough. Okay, so we can relate V to I2. So we can turn all of our I2s into V's. So then these two equations here are just in terms of V and I3. And so from there we've got two equations, two unknowns. We can simplify them, or we can solve them simultaneously, and then we can find V. So I'll do that right now. So I'll move this to this side and I'll collect these terms. So what we've got is that V is equal to 1 on 4. I'll start with V first. I won't do that. I'll keep the bracket open so that I can build it up. That's 1 on 4. We know I2 is equal to V on 5. So this is going to be 8 on 5 plus 4 on 5. So what that's going to be is that 8 on 5 plus 4 on 5, that's 12 on 5. Plus 12 on 5. Are there any more I2s? Taking that. No, we're good. So we've got this, and then that is going to equal, let me just move this to the other side so I don't confuse myself. I've just taken the -4 and moved it to the other side. And then we've got, so that's V, and then we've just got I3s left. So we actually just have one I3. Brilliant. Minus 2 I3 is equal to 4. Great, that's an I. Okay, and then from there, I can get rid of this. This is not important because we've got that. Okay, and then we can put all of these values for I2 into all of the I2s in there. So what I can find is that we'll start off with the V's similarly. So we've got 1V minus 1 on 4. So that's going to be 3 on 4. That's 3 on 4. Then we've got I2. We've got minus 8. So that's minus 8, and then we divide it by 5. Minus 8 on 5. I2 from there. And yeah, that's all right. That's all for V. And then we can do I3. We don't have any constants in this equation, so it works out quite nicely. So then for I3, we have 2 minus j. And that's equal to 0. There we are. And I can get rid of all this. So we've got this, we've got that. We can get, so what we want to find is we want to find V. There's no point finding I3 because that's not what we care about. We just want to find V. From there, we can get I3 in terms of V, and then we can plug that into our first equation. Then we can get V directly. So I3 is going to equal, that's going to be V times, I can actually, I didn't solve that, but that's fine. I'll just do minus 3 on 4 plus 8 on 5 divided by, so I've flipped the negatives of this because I moved it to the other side, and then I'll divide by 2 minus j. Alright, and then I'll take that and I'll put it into the first one. So it's going to be V times 1 on 4 plus 12 on 5 minus 2. We've got I3, so we'll put that in. So we get V minus 3 on 4 plus 8 on 5 on 2 minus j, and that's going to equal 4. Oh, I'll move losing a bit of space. Can you see the 4 at the end? Hopefully. Or just, if you can't see it, there's a 4 at the end. Okay. And so from there, I think I'll start simplifying from now because these fractions are getting out of hand. And so we can just get, this is a v right here, this is a v, everything else is just numbers, so we just rearrange and we find v, essentially. So I'll just do that in my calculator right now. So we've got 4 plus 12.5 minus 2 times. And this is going to be okay. 2 minus I. Yeah. Great. So we get 2.00 whatever, angle 9.79. And so our v, our actual v, in the time domain, let me rub out some of this garbage that I don't care about anymore. So from here, v of t is equal to 2.0 cosine, we defined it for cosine, 3t, and that was positive 9.79 volts. All right, and that was that problem. Yes?
Is that in degrees or radians?
That is in degrees, sorry. My bad, I should have specified. That's in degrees. Are there any questions about this? No? Okay, great. I think I spent a lot of time on these questions. I'm gonna move on. But the next part, so I think that's the last of our transformer problems. So the rest of them are just going to be transient, which is not nice, but we'll make do. All right. Oh, there we go, transient analysis. Okay, so here are some of the definitions for the circuits. First order circuits, we did that in quad 1, if you remember. So that was our capacitors and our inductors. We have a general solution for them, if you remember, or you can solve a first order differential equation. A lot of these are separable, so you can divide one across and there would just be, the integral will be at ln, and then you take the exponential of that, and then you'd get a decaying exponential. That's for a natural response. In 2134, we've introduced second order circuits, and those are circuits that include both an inductor and a capacitor. And these are a bit more complex. They can have multiple different sort of forms. Some of them can be underdamped, overdamped, critically damped, depending on your characteristic equation, which we'll find. And so we'll find the characteristic equation based on these two coefficients. All right, so transient analysis procedure. I'll just go over this while I'm doing the problem. There's no point actually explaining it right now. So it's just more procedure. Is finding KVL, KCL. Okay, so it's just finding the differential equation, which is a bit finicky. And that's just our first question. Awesome. So I'll just do that. This is a problem. It's from the 24 paper, term 1. Yeah. And so what we find is that we need to find I of t that represents this circuit at t is greater than 0. Does it also ask for it at equal, is it just equal to 0, or is it including the That's more conditions. Oh, all right. That's the same question, but we need to find the initial conditions. All right, we'll start off with that because that's easier. Okay, so we've got this circuit. We know that the switch is closed at before 0, and then when it opens, or when t is just at 0, then it opens. And so the voltage source is disconnected. So before then, our voltage source is connected, and because we have a DC source, all of our inductor and our capacitor are going to be operating at DC conditions, so the capacitor becomes an open circuit, and our inductor becomes a short circuit. So I'll just draw that. So I'll just draw it for t is less than 0. So when t is less than 0, what we can find is that this is the circuit. The capacitor is an open, actually I'll draw that later. This becomes our resistor. Plus minus 30. Yep. Okay. So we'll call this plus minus VC, and this is going to be our current for our inductor. IL. Now what I've done here is that our inductor becomes a short circuit and our capacitor becomes an open circuit. And so what we can find is that we want to find the current going through here. There's no current going through here anymore because it's an open circuit. So it's just going to be, there's 30 volts. This was 2 ohms. So it'll be 30 on 2, that's 15 amps going through there. And if we want to also find the initial condition for the voltage, if it did ask, it doesn't ask, but we'll use it because, we'll find it because it's useful for the second part. So this is just going to be, these share the same terminals, so it's just going to be 30. So what I'll say is that IL at 0 minus is equal to, well, I mean IL at 0 plus, but we'll get to that later. And that's equal to 15 amps. Our VC at I minus 0 is going to be 30 volts. Okay, I'm losing chalk. I need to find another one. Great. So that's the first part. Then the second one is that we have to find the derivative. Now when we find the derivative, a lot of people find this quite difficult. What I like to do in order to find the first derivative is that when we're doing that, we don't want to look at the first or the circuit at before t is equal to 0. We want to look at it just after the switch opens. So if I redraw it, so I'll get rid of this. If I redraw the circuit, the voltage source is not important anymore. Our inductor still exists. This is 2 ohms. This is a capacitor, right? What we know is that, given this, we have our current source. We still have the same current going through this. This is at, let me change that. This is at t is greater than or equal to 0, but not at infinity. And so what we find, right, is that here the current is still 15. Here the voltage is still 30 volts. And so the current through there, we can find the voltage through this. So the voltage through that is going to be 30 volts. So there's 0 volts going through this. Or this contributes 0 volts to the circuit, essentially. And so given our equations for inductors and capacitors, we know that inductors are given by V of L is equal to L dIL of dt. We can find VL, because we know that this is 0 volts. This is equal to 0. This inductance doesn't matter. So we know that D of IL at 0 minus, which is same as 0 plus, this regard, is equal to 0. You guys see how I've done that? I just sort of used the definition that we're given. Now, if I wanted to find the capacitor, right, it doesn't ask us to find the first derivative of the capacitor at 0 minus, but if they did ask, the way I'd find it is that, well, we know I of C is equal to C dV C on dt. We want to find this quantity, but IC is just the same as the current going through this. is just one mesh, right? So this is equal to 15. So d of VC of 0 minus, I'm running out of space. Let me just draw that a bit higher. D of VC 0 minus on dt is going to equal, it was 15 on whatever C was, which was a half. Okay.
Quarter.
Oh, quarter? Quarter. Thank you. So that would be 60. This would be 60. And then blah, 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 if you need to find more stuff about that. That's the first part of the question. What we'll do is that we'll save the important quantities that we found. So, yeah.
60 or minus 60?
Good point. This is positive, this is negative. This count's going, oh wait. Yeah, it's minus 60. You're right. The reason it's minus 60, my bad, is that at this node, the current, this voltage, or the current through this, is defined for here. But this current's going this way, so this down here is minus 15. And so if you do the same calculation, now it's negative, and then you get negative 60. Sorry, good catch. I didn't see that. Luckily, it's not important for this problem, but if it was, that wouldn't be bad. Okay, so we know first derivative of IL, and we know our IL. I'll just write these up here. Actually, no, I don't need to. It's right there. That's good. Okay.
Sorry, you are just rubbing it out, but I was just wondering why the voltage over the
Oh, I'm sorry. I should have.
resistor is 30?
Of the resistor.
Yeah.
Okay.
And T is
Maybe I can just point to this, if that's okay. All right. So what we found before this was switched open is that we knew that this was an open circuit, and so this shares a node. These nodes with this, so this is 30. Can you see how the voltage across the capacitor is 30?
and then when we put the switch on,
Yeah. So sorry, what was your question again?
why?
Lost.
Oh, okay. I don't think it's alright.
No. You can ask it. What was?
Well, I was
just lost
wondering why when we look at 0 plus, T equals 0 plus, why the voltage over the resistor is 30. But
Oh, because it's a capacitor, so it has to control. Its voltages doesn't change abruptly. So whatever's at T minus.
The 2 ohm resistor.
Oh, the 2 ohm resistor. Sorry. Yeah. Okay. So that's 30. If I just redraw that, so the way they did it, I'll just do it quickly. This becomes essentially almost like a source.
Okay.
This is 15 through there. This is 30. This is 2 ohms. I times 2
Oh, okay.
is 30.
I see.
And so it's sort of conserved. That's 30, that's 30. This has nothing going through it.
Right.
Does that sort of make sense?
Yes.
I've just done 15 times 2, essentially. I think I'm going to have to redraw it again for the next part. So like, all right. So that's the standard form for our ODE. We'll get to that in the second part, but you can see those are our coefficients for the characteristic equation. They're related to the Neper frequency and the natural frequency, which sometimes is also our resonant frequency, which is pretty interesting. It's related to poles and zeros, if you want to read more about that. And so those are equations that specify those. Okay, and then there's damping. So that just depends on the roots of the characteristic equation. If they're both complex, it's underdamped. If they're both real but they're distinct, then it's overdamped. But if they're real and they're like a double root, then they're critically damped. Okay, and so that's just sort of the process to find the ODE, but that's fine. I'll just go over it and I'll explain as I go. Okay, so just find I of t at t is greater than 0. Great. That's enough. That's good. Okay, so we need to find the current I of t. And so what we know is that when we redrew this circuit, interestingly enough, I'm going to have to draw this again, but bear with me. This is a resistor. This is 2 ohms. This circuit's actually quite nice, because what you can see is that this is just series RLC, right? And so, I mean, I already know, if you've done a lot of problems like this, you'll see that the equation for this is always going to be IL dash dash plus R on L, IL dash plus 1 on LC, I is equal to 0. I just know that. But I'll derive it for you guys, because you'll have to during the exam. You can't, I don't think you can just quote this. But it's a good sanity check, essentially, because you already know what the answer is supposed to be. Why did I drop that out? That was 0. IL 0 minus, I'll just switch my notation to this. So this is just prime, just because it's less difficult to write than the actual derivative. And that's 0 amps. Okay, so we can find the equation to this. This is C, this is L. We can do KVL. So we want to find, we know our equations. It's going to be, we know I is equal to C dV dt. I always like writing these on the side just so I don't forget how the properties relate to each other. And then I've got V is equal to L di dt. Can you guys read that just in the corner? Yeah. And then, so we've got these two properties. What we can say is that we've got VC plus, that's going to be VL plus IL R is equal to 0. That's just doing KVL. These are all passive sources, so we can just define them to be positive. You just do like positive, positive, and then this is positive, negative, negative, negative. Great. Now VC is here. VL is there. This is IC. That's VL. And so what I can do is that I can take the first derivative of this. So I can say this is VC dash plus VL dash plus IL dash R is equal to 0. VC dash, this is VC dash, as multiplied by C to get IC. IC from the circuit is the same as IL, because it's one mesh, right? So what we can say is that VC is going to be IL on C, because that was IC, and I just made it IL, because they're equivalent. And then we've got VL, the derivative of VL. That's just going to be the first derivative of this, so this becomes the second derivative in terms of IL. So that's going to be plus L, IL double dash. And then this stays as IL dash R is equal to 0. And so we want the second, for the standard form, we need to get rid of the coefficient for the first, second derivative. So this is second derivative, we divide everything by L. So we can get, just write that here. So we get IL dash dash plus, it's going to be R on L plus R on L, IL dash plus IL times 1 on LC. 1 on LC, IL is equal to 0. All right, that's great. That matches perfectly with this, so you know it's correct. A lot of papers you'll find that they like to give you Because transient is usually quite difficult, they don't want, at least maybe INMA, might not want you to analyze a really super convoluted circuit. So a lot of the times, they'll reduce to either all parallel RLC or all series. And so it's usually a good idea to know what the form of those equations are. If you want to know the one for parallel RLC, it's going to be IL dash dash plus, it's 1 on RC, that's IL dash plus 1 on LC, because it's the same resonant frequency. That's the general solution for parallel RLC. And then you can just swap the I's for V's if you're doing for capacitance. There's a proof in the textbook if you need to see, but it's good to just have these in your head, just so that you know, okay, when I'm doing my questions, I know what answer I'm supposed to get. Not that you can quote these, because you can't. Okay. So, we want to find the solution. We've got everything in terms of L and R. We want to find the actual coefficients, so we'll call this A1. This is A0. A1 is equal to R on L, which is equal to, what's R? R is 2 on a half, so that's 4. And we know that A0 is equal to, that's going to be 1 on LC. L is a half, C is a fourth, a half times a fourth is 1/8, so it's going to be the reciprocal of that, so that's 8. Mental maths. Okay, where's my eraser? Here. Alright, so we've got these. Now, in our formula sheet, they actually give us, thankfully, the forms of the root. What was the, where's underdamped and, well, it doesn't, I'll just recall it then. That's fine. Okay, so we know our characteristic equation uses those coefficients. So it's going to be s squared plus 4s plus 8 is equal to 0. This looks like it's going to have complex roots, but I'll just verify it. What you can do is that you just use the quadratic equation, or you can complete the square and then take a square root, like they've done you can see in the first line, but it's not overdamped, it's going to be underdamped, but I'll show that in 1 second. Oh, where am I? Here we are. Not so much chalk on me. All right, so I'll just use the quadratic equation. So we got -4, we know, I'll just write out the equation if you don't fully remember it. So that's going to be minus b plus minus square root of b squared minus 4ac on 2a, where a is 1, b is 4, and c is 8. So if you just whack that into your calculator, you'll get 4 squared minus 4 times 8 times this on 2a. Okay. So that's going to be -2 plus minus 2j. They're conjugate roots because these are real numbers. Okay, so these are complex values, so we know it's going to be underdamped. And for underdamped circuits, we know the general solution. We can get rid of this now, it's not useful anymore. Neither is the circuit, actually. Okay, so we know our underdamped equation is going to be IL is equal to e to the minus alpha. Ooh, I don't have the. Do you have the formula sheet?
The formula sheet for alpha is on the other side.
Of where? Back?
There, in the corner. A1 and forward one.
No, I need the actual other one. The one from the formula sheet. Oh, there we are. There we are. Okay. So that's the general equation for this is going to be, that's times t times b1 cosine of omega d t plus b1, is that b2? Yeah, it's b2 sine. B2 sine of omega d t. We know that S, oh, actually no. We know that A1, based on our earlier definition, where was it? It's up here. Nope, too far up. We know, where is it? Well, it's actually supposed to be there, but I didn't write it down. We know that A1 is equal to 2 times alpha. I think it was up there, I just kind of didn't find it. And that A0 is equal to, A0 is 1 on LC. So therefore, our Wn is equal to 1 on the square root of LC. And so we know what A1 and A0 are, so we can find Wn and alpha. So alpha is going to be equal to, we know A1 is 2, I believe. Where did I put that? No, A1 was 4. A1 was 4. So alpha is going to be 2. And then we know that omega n is equal to square root of 1 on LC. So it's going to be the square root of, sorry?
Square root of 8.
Yeah, that's fine. 2 root 2, right? I think. Yeah? Wait, I need it. I don't usually do this. Yeah, 2 root 2. Okay, so we've given that. And then we want to find WD. We actually don't need to find Wn because we've got it squared. So that's going to be 8 minus, that's going to be 2 squared, so that's 4. That's square root of 4, so that's 2. WD is 2. And we need that for this and this. So if I just rewrite this, we know that alpha is equal to 2. IL is equal to e to the minus 2t. We don't know what b1 and b2 are, but we know that cosine omega d is equal to 2t plus b2 sine of 2t. Okay. So that's our general equation. We know that this is a natural response. We don't actually have a source in the second part, or when t is greater than 0. You can see here when we open the switch, this is disconnected, so it's decaying. There's no the steady state of this would be 0. So we don't have to worry about a forcing function or a non-homogeneous equation, essentially. And so we have IL. We have 2 coefficients here that we don't know, but we know these initial conditions, so we can find what these are. So we know that IL at 0, so this, when I put E is equal to minus 2 times 0 times B1, we know cosine of 0 is 1, this is times 1, plus we know that B2, or sine of 0 is 0, so we don't even have to worry about that, that just becomes 0. This e to the 0 is just 1, so this just becomes 1. So we'll get B1 is equal to 15. Nice. B1 is 15. Now for the second one, it's a bit more difficult. We've got I1, we've got IL, but this is a condition for IL's, the derivative of IL, so we have to take the derivative of this. Now, you can expand it out and then take the derivatives. I'll just do product rule, if you remember that from maybe high school. So IL dash is equal to, we'll take the derivative of the second one first, so we'll do e to the minus 2t times, this is going to be minus 2b1 sine of 2t, too quick, minus sine of 2t, and then sine becomes cosine, so plus b 2 or 2b2 of cosine of 2t. I am losing space, but that's fine. That's the first part, and then just take the derivative of the second one. So that's going to be minus 2e to the minus 2t, and then the first part stays the same, or the second part stays the same. Sorry. Yeah, so that's 2t plus b2 of sine of 2t. Okay, so that's a mess, but we can sub in t is equal to 0, and we know that all of this should equal 0. So this is equal to 0. So what we get is that this goes to 1, because it's an exponential. That's 1. Sine of anything is 0, so or sine of t is equal to 0 is 0. So that's 0. That becomes 1. So this just becomes 2b2. Let me get more space. Actually, right on the left. Okay. So that's 1, that's 0, that's 2b. This also goes to 0 because t is 0. So this exponential goes to 1. Actually, pardon me, that's 1. This goes to 1, and this goes to 0. Okay, so if I just rewrite that, what we get is that 2b2 minus 2. So this is 1, this is 0, this is 2b, minus 2 times b1, and that's just 0. Minus 2 times b1 is equal to 0. This is 15. So we move that across. That's 30. 2b2 is equal to 30. b2 is equal to 15. All right, and then we're finally done. So if I just rewrite, we've got all of our unknowns. So we know b2 and b1 are 15. So we know that IL is equal to e to the minus alpha, which is 2t, times, I'll take out the 15, because b1 and b2 are both the same, and this will just become cosine of 2t plus sine of 2t. Amps. And that's in the form of, well, it's actually not here. It's going to be in the formula sheet. But are there any questions about this? This is the answer. Yeah.
The A is the amps, right?
Sorry?
The
Yeah,
amps.
that's the units. Sorry, probably should have been more. Yeah. Okay. All right. How am I doing for time? Maybe we should just move on to your part. I can maybe explain the next part quickly on how you would do it, but I won't actually solve it. This is a textbook question. Yeah, I'll just explain how you do it because we have to move on. All right. So this is another transient problem. We need to find for t's. Let's cut off. Let's be t is less than 0 or greater than 0 and greater than 0. So it's just a complete response. So what we have is that we only have a capacitor here. So this is a first order ODE. So we wouldn't actually use our equations that we found here. This is different. This is actually simpler to solve. So what we can do, let me just zoom in a bit. What we do is that we can find the initial condition for, we need to find I. So you find the initial condition of I. We know that this first is closed, so you get the voltage, or you have to do a bit of circuit analysis, but you can find the value of this. And that will be I need to write this or I'll lose where I am. All right, so then you can find whatever I L at 0 minus is equal to, and that's whatever. And then that's the same as I L at 0 plus. And then when you open the circuit, you just have a capacitor, and then you have this, and then you would analyze this. Now this has been charged up from the voltage source. So what you can say is that this is actually given by, yep.
Is that meant to be a current source?
Sorry, my bad. That's a current source. But it's not too important for how I'm sort of explaining it. What you'd say is that if you want to find the voltage across, or you want to find I, you'd find the voltage across the capacitor here. So know that, oh, this is breaking apart. This is going to be Vc is equal to Vc e to the minus t on tau. You guys remember this from quad 1? So it's just that. This is a general solution. If you wanted to, what you could do is that you could create the first order ODE. I don't think this one is separable, so you might have to use an integrating factor. If you've done math 1, 2, 3, 1, that might be familiar. But don't worry about that. All you have to do is just find this. Tau here is RTHC. RTH is as seen from the capacitor. So you would open circuit this and, you've got a dependent source. So there's a bit more to this problem. This is a dependent source. So you'd have to use, if you can remember from quad 1, it's method 2 or 3. So if you're going to use method 3, you'd add a voltage source here, calculate the current going through it, then you can divide them, and then you can find RTH, which is this. You already know what C is. So we found this, we have T. You want to find VC. VC is just going to be 80. Actually, it's not going to be 80, but that will be what you found previously. It was back when I was explaining that we had to find I, you also have to find VC. That's the initial condition, because this is going to be VC of O minus. There's actually a bit more analysis you have to do before you apply the switch. And then you would have this equation right here. And then, but you don't want to have the voltage across the capacitor. You want to have the current through the resistor. So what you would know is that this circuit here, this is going to be VC. This is I, right? So that's just going to be V is equal to I times, I is going to be times R, and that's going to be VC. So we know what VC is, we know what R is, and then we can get I in terms of the time domain. Sorry, this is a bit hastily gone through, but hopefully like my thought process kind of makes sense. It's a textbook question, so you can just you can find solutions to this, or I can upload the solutions afterwards. All right, we should probably move on.
Okay, so now we're going to move on to Laplace. So, how do I use this thing? Guys? Zoom out? Okay. Oh, okay. Thanks. Eraser. So in the first half of this course, we learned about the Fourier transform, and we generalized the Fourier transform using the Laplace transform. So the form of it is quite similar. We just take the integral from 0 to infinity of f of t times e to the negative st. And one thing that's kind of important to note is that s is actually just sigma plus j omega. So the Fourier transform is really a special case where sigma equals 0. Okay. So in the formula sheet, we have a bunch of Laplace pairs that we can use. So you're not expected to actually use the definition all the time, right? You can just look at your table and then convert them as you like. So let's look at a simple example where we have to look at the table. Actually, you know what? Let's do this one from the definition, because sometimes you will have to use the definition for some questions. So let me write down the definition. So we have that the Laplace transform of some f of t is denoted as f of s and is equal to the integral from 0 to infinity of f of t times e to the negative st with respect to time. And I guess I should also include the minus. So the question is asking us to take the Laplace transform of e to the negative at. So what we can do is sub that into our integral and attempt to evaluate it. So we have e to the negative at times e to the negative st dt. What we can do is we can make this e to the power of negative t times a plus s with respect to t. Okay. Now the integral of this is going to be simply 1 on a plus s times e to the negative t times a plus s evaluated from 0 to infinity. So if we evaluate the bounds, if we sub in infinity, you can see this is e to the power of negative infinity. This ends up tending towards 0. And then we have minus, we sub in 0 into the exponent and we get 1. So these cancel out. And we're left with just 1 on as, a plus s. So that's actually our first and probably one of the most important Laplace pairs that we'll see. That the Laplace transform of e to the negative at is 1 on a plus s. And we can refer back to our table. Oh, 1 on s plus a. They have it written down, but same thing. Okay. So during the exam, you will be expected to derive other things, but you just use the same process, solve the integral, and it's not a major part, so we'll move on. So two important properties that are often mixed up are the shift properties. So the time shift and the frequency shift. So the time shift just means that we have taken our function f of t and shifted it in the time domain, whereas the frequency shift means the same thing but for the frequency domain. So let me write these down. We have that, so this is the frequency shift. We have that f of, is it t minus a times u of t minus a transforms, using the Laplace transform, to e to the negative as times f of s, where f of s equals the Laplace transform of f of t. And then we have the time shift. Sorry, this is actually the time shift. Then we have the frequency shift. Which is e to the negative as, at, times f of t. Let me just check this. Yes. Transforms, using the Laplace transform, to f of s plus a. And so we have a shift in the frequency domain. Okay, so let's actually see how we can apply this to a question. So we're given that the Laplace transform, and this is given in your formula booklet, by the way, of sine of just t. Sine of t equals 1 on s squared plus 1. We now want to find the Laplace transform of e to the negative 10t times sine of t. Okay, so which property does this kind of fit in with? You can see that it kind of fits the form of the frequency shift, where a equals 10. So we can just match it up. So we have that a equals 10 and f of t equals sine of t. Therefore, f of s of sine of t is 1 on s squared plus 1. But now, this is actually equal to f of s plus a. And so using this, we can just sub in s plus a into s. 1 on s plus a squared plus 1. Okay. And this is also kind of given in your formula booklet. So there are some other Laplace properties which are not used as often. However, time differentiation is quite important. Linearity is extremely important. And we'll use these as we go through the examples following. There's also frequency differentiation, initial values, convolutions. Convolutions we'll talk about later. Okay, let's just do a simple example where we find the Laplace transform of a more complicated, what do you call this, function. So this actually came up in Lath's example before. So we have 1 on s squared plus 4s plus 8. Now, the first thing to do is, well, the first thought that you might have is that this could decompose into like s plus a plus 1 on s plus b, something like that. But the only way that this is possible is if we are able to decompose this quadratic into two factors, yeah. So what we have to do is we have to actually check the determinant of the quadratic and check that that we can factor it into two real components. So the determinant is 4 squared is b squared minus 4ac. So b comes from here, 4 squared minus 4 times 8, right? And this is going to be 16 minus 32, which is negative 16, which is smaller than 0. So since this is smaller than 0, we cannot actually decompose it into two factors like this, unless we have imaginary a and b. So we don't want to do that, because that's just painful. So what we're going to do instead is we're going to use completing the square to try and turn this into a form that we already know. And that form is, if I go back, the sine and cosine forms. Wait. Yeah, sine and cosine forms. So we can complete the square of the denominator and get something like this, s plus a squared plus omega squared. And we have to kind of match it up and just make it work. So let's go back to the question. Finding the inverse Laplace of this. Actually, why don't I leave the formulas up? Yeah, okay. So we want to complete the square for this one. So what we can do is, this is s plus 2. So we can divide the b term by 2. S plus 2 squared minus 4 plus 8. So this just ends up being plus 4. And in the form here, you can see that the omega here is actually squared. So for that reason, I'm going to write this as 2 squared. Cool. Now, you can see that it matches up with these two forms really well. And we have to figure out which one to use. Well, we don't see any s's in the numerator, so I reckon we'll use this one. So we want an omega on the top. Now omega equals 2, right? But there's no 2 here. So what we can do is we can actually just force a 2 in. We can just make the 1 a 2 divided by 2. And then we can take that divided by 2 out, like this. Now it does match the form exactly. So this is our f of s. Okay. Now we can take the inverse Laplace transform using the pairs. So our f of t actually becomes 1/2. So this is using linearity because this is just a constant multiplied by our thing. So it's going to be 1/2 times, and going back to the pairs, we can see that it matches up with sine e to the negative at sine omega t. So this is e to the negative 2t, where a equals 2, negative 2, wait, a equals negative 2, no, just positive 2, e to the negative 2t times sine omega t, where omega is also 2. So sine 2t. Yes. Okay. Any questions? Okay. Okay, and now let's do some Laplace applications. So all of what we just covered was kind of the basic skills that you need to perform circuit analysis on Laplace transforms. But now we actually look at Laplace transforms in the context of circuit analysis. So given a circuit analysis question that requires Laplace transforms, you can always follow this 4-step procedure. So this actually applies to the vast majority of questions. Step 1, find initial conditions. You saw in Transient that this was also an important step, finding the initial conditions. Step 2 is to convert every element into the S domain. And this includes initial conditions. So I'll get into how to do that in a second. And step 3 is just quad 1. So you should know this from ELEC quad 1. You just perform circuit analysis as if you just had resistances and sources and stuff like that. And it's fine, and it works. And finally, we have to use the inverse Laplace transform to convert back to the time domain. And in order to do that, you have to use partial fraction decomposition. So just turning your fractions into like 1 over s plus a terms, stuff like that. And get it into forms that you can convert back using the Laplace table. Okay, so let's look at an example, just to start off with. So in this example, we have some sort of switch, which represents the change at t equals 0. And we want to find the output voltage, so V0. So I'm going to redraw the circuit here. Circuit looks like this. We've got a 10 ohm resistor, 5 ohms, 1 Henry, and 10 millifarads. And we also have the switch over here. Yeah. And the voltage across this capacitor is V0. And this is 10 millifarads, yeah. And ground here. Okay. So let's go back to our steps. And maybe I'll actually write them down. The first step is to find the initial conditions. Can you see this from here? Yeah, it should be fine. First step is to find the initial conditions. Then we convert to S domain. Then we just do circuit analysis. And finally, we use the inverse Laplace. Okay. So let's follow this 4-step procedure on this question. So let's first find the initial conditions. So the initial conditions is quite simple. We'll redraw the circuit. So just like in the transient, we redraw the circuit at time t is less than 0, but we turn all of the inductors into wires, and we turn all the capacitors into open circuits. So this inductor becomes a wire, whereas this capacitor just becomes an open circuit with the voltage V0 across it. And what we have to do is we have to find the current through this inductor, as well as the voltage across the capacitor. And this is 10 ohms, and that's 5 ohms. So let's actually start with the voltage. You'll notice that, it's grounded, right? You'll notice that the top, like one terminal of the capacitor and the other terminal of the capacitor are both the same node, meaning that the voltage difference across it is 0. So this is my favorite part, because it's so easy. Then what we do is we have to find the current through the inductor. And the way that we can do this is using current division. I normally don't like current division, but what you can do is you can actually take the admittances of these and then do voltage division, kind of. So I'll explain what this is in a second. So you take your input current and then you voltage divide, but with the admittances. So we have 1 on 10, so that's like our target branch, divided by 1 on 10 plus 1 on 5, which is like the total resistance. Does this kind of make sense, what I've done here? Okay. So anyway, like even if you don't know this, just use voltage division, or you could even do a current division, or use a source transform and find this somehow. But anyway, we can multiply the top and the bottom by 10, and we cancel this out to get a 1. On the bottom we cancel these out to get a 1 plus 2. So in the end we have 3 divided by 3, which is just 1 amp. So the initial current is just 1 amp. Nice. Okay, so I'm going to write that down over here so I don't forget it. The initial current is 1 ampere, whereas the initial voltage, the output voltage, is 0 volts. Okay, and let's erase this. So what we've just done is we've found the initial conditions for this circuit. So we can write a check here. Done. Step 1. The next step is to convert the entire circuit into the S domain. So this step is a bit more confusing, but it's still okay. So let's start with the current source. So if we go back to the Laplace pairs, you'll see that any constants actually become that constant divided by S. If it is here, yes. So constants, okay, so we have to think of it like 3 u of t, kind of. So since it's 3 u of t, this matches up with the u of t pair, meaning it becomes just 3 on S. Nice. Now, this is actually after time t equals 0. So what we have to do is make sure that this switch is closed, meaning that we completely bypass this 10 ohm resistor. The 5 ohm resistor stays the same. And the inductor, let's actually do the capacitor first. So let's do the capacitor first. So we use that the impedance of the capacitor in the S domain is 1 on SC. And we know that the capacitance is equal to 10 millifarads, which we can write as 10 times 10 to the power of negative 3, or 10 to the negative 2, or 1 on 100. So then the equivalent impedance is 100 on S. Okay. 100 on S. Now the inductor, we can use something very similar. So by the way, just a side note, this actually matches up with the Fourier definition which we used in the first half of the course, which is 1 on j omega c. It's just that S does, in the Fourier version, there's no sigma component. So remember, S is equal to sigma plus j omega, right? Okay, cool. So in the same way, we can actually convert the inductor into the S domain using that the impedance of the inductor is S times L. In this case, L is just 1, I think. It's just 1, yeah. So the equivalent inductance, equivalent impedance is just S. However, we do have initial conditions here. So we can't just do this. So we have to do something a bit weirder. So what we'll do is we'll go back. First of all, let me actually write down Ohm's law for inductors, which is that the voltage across an inductor is equal to L, which is the inductance, times the derivative of the current going through the inductor divided by the, with respect to time. So what we can do is we can actually take the Laplace transform of this equation, and we get, and so this is in time domain initially, but if we take the Laplace transform in S domain, we have that the voltage across the capacitor is equal to L times the Laplace transform of the derivative of the current. Okay, now how do we do the Laplace transform of the derivative of the current? I have no idea, but the table has an idea. Where is it? Wait, too far. Okay. Here? No. Here, okay, time differentiation. So, the Laplace transform of the derivative, the first derivative, is equal to S times the Laplace transform of the function. So remember, this is the derivative of the current. So it's S times the Laplace transform of the current minus the initial current. So I replaced all the S's with currents, the F's with currents. Okay, and I should specify that this is through the inductor. Now, what we can do is we can expand this out a bit. So I'm going to get rid of this now. We can expand this out a bit, and we have that the voltage across the inductor is equal to SL times IL of S minus L times IL of at 0. Now, the way that we're doing the analysis, you can see that it's mostly in parallel, right? We would prefer to have current sources rather than voltage sources. So what I'm going to do is I'm actually going to solve for IL, and you'll see something interesting happen. So we solve for IL. So this one came from here. I'm erasing it down. We solve for IL, and we get that this is equal to IL, so the initial current divided by S, plus the Fourier transform of the voltage divided by SL. Now I'm going to rewrite this one as voltage divided times 1 on S times L. And you'll notice that this is actually the form of Ohm's law. So I'm going to write it like this actually. This is actually Ohm's law. So this is actually, this gives us part of the current. But we can see that there's another component of the current that comes from the initial conditions. So this part is as normal. We can write our inductor as S. Oh, because L is like this, 0. Okay, we can write our inductor as S. But then we also need to include this thing. So the current through the inductor is going this way. So we need to add in this initial current divided by S, which is, in this case, 1 on S. And remember, this is a current, so we're going to add a current source. Like this. Okay. So now we can perform circuit analysis. Well, okay, first of all, we have converted the circuit to the S domain. So we can now perform circuit analysis, just as in quad 1, on this circuit. So what are we trying to find? Oh, sorry, one more thing. We also have initial conditions for the voltage. However, in this case, we have 0 initial conditions. So if we do the same process, that extra constant term will actually cancel out. So we're not going to do that. We don't care about it. Okay. So we perform circuit analysis, just as in quad 1, to find the output voltage. Okay. Now there's a number of ways you can do this, but my preference here is actually KCL. So we'll label these currents as going downwards. I'll just ignore that one. We'll label these currents as going downwards. And we can perform KCL on this node. So, which currents are going in? The only current going in is this, 3 on S. And then the currents going out are these ones. So, remember the voltage at the top node is V out, since it's the voltage across the capacitor. So that means the current going through this resistor is going to be V out divided by the resistance. Okay, similarly, we can just treat this S as a resistance. So let me just, that's a 5, not an S. And we can treat this as a resistance as well. Oh, no we can't, sorry, that's just a source. But we can treat this as a resistance. So what we do now is we have to solve for the output voltage. So let's do that. We have 3 on S minus 1 on S, that's just 2 on S, equals, and we'll group all of the, I'll move this to the top first. We'll group all the V outs together. We have 1 on 5 plus 1 on S plus S on 100. Cool? We'll turn this all into one fraction. So we'll turn this all into one fraction and then solve for V out. So we move that to the other side, 200 on S divided by S times 20, I should write S squared plus 20S plus 100. And very conveniently our S's cancel out. Okay, cool. Now I'll rewrite this equation over here because I'm running out of room as V out equals 200 on S plus 10 squared. So it's just S plus 10 squared, which is quite good for us because this matches up with one of our Laplace pairs, which I have to find. This one at the bottom. So 1 plus S plus A squared, so A equals 10, transforms to T e to the negative AT. So using the Laplace transform, this expression becomes 200 T e to the negative 10t. Yeah. Okay. So that is the response in frequency domain. So V out of t. So we'll go back to the question. That's the answer for this. Cool. Any questions? Okay.
Where does the current source come from again?
Okay, where does the current source come from? That's a good question. So this is probably the most confusing part of this. it turns out that when you have initial conditions in an inductor or a capacitor, you can represent that as a constant DC current source in the frequency domain, which is really weird, honestly. Like, it's pretty unintuitive. So let me just go through it again, just very quickly. We have that the voltage across the inductor is equal to L times the derivative of the current with respect to time. And what we can do is we can take the Laplace transform of both sides. So I'll just speed through that again. We take the Laplace transform of both sides. And then we get this expression. So if you remember in the lectures, at one point Inma talked about putting, do you remember like putting DC sources into the, like, as initial conditions? Do you like recall this? It was very, very quick. She just went through it kind of slightly, which is okay. But it's quite useful for solving some of these questions. So what we can say is the voltage across so if we leave it like this, we can think of it like this. We have some inductor, like this, and some volt VLS over the inductor, right? And some current I of S going into the inductor, right? But what this is saying is, this is actually just a kind of, it's quite similar to KVL, but it's kind of hidden, right? So if I redraw this, it's like this. You go into this node here, and this is your SL times I of S. So does this make sense where this comes from? SL is like the impedance, and I of S is like the current, right? So impedance times current, what does that give you? So V equals IR? Yeah, so just V, right? Yeah. So that gives you the voltage across this inductor by itself, right? Then there's also this other term, right? Like, how do we deal with this? So this is actually, remember, we're looking at voltages. So we need to add in another source. We need to add in a source, but it's negative this time, so it's minus. And the value of it is L times I initial. Does this like kind of make sense, what I've done here? Like, if you just follow, like, forget about the meaning behind it for a second, but if you just follow the maths tells you that you have to have an initial condition at this point, right? It tells you that there has to be some sort of source here. So remember, the way that I got to this, just to recap, is that we started with Ohm's law for an inductor, which is that the voltage across an inductor is equal to L times the current, the derivative of the current with respect to time, right?
Okay, thanks. That makes more sense, but then how do you get it to a current source?
Oh, so how do we actually put it in? Okay. So what we have to do now is, well, we're kind of looking at this in parallel, right? So I've decided, okay, I don't want to do this. I don't want to add in another voltage source, because that's like, it's pretty annoying to deal with, right? Especially when everything is in parallel. So I've decided, okay, I want to solve for current. Because it turns out that when you solve for current, it'll make you add in a current
So it
source.
does the same thing, but it adds in current source.
Correct, yeah.
Okay.
It does the exact same thing, but with a current source instead of a voltage source. Does it kind of make sense? Yeah, cool. All right. So, by the way, you can just memorize this as well. This is just the reason behind it. If you ever forget it, you can just do this. Because I'm not going to remember it, honestly. So, the next question is this. How are we doing for time, by the way? Okay. All right. So in this question, it's no longer a DC source. In the previous question, we just had a DC source. We now actually have some variable source. And this variable source has a step response. Oh, I should keep this. So this variable source has a step response. It goes to 3 volts, and then after 1 second it goes back down. So let's draw out this circuit. And before I do anything, I'm actually going to try and turn this step response into maths. So we can actually write this as 3u of t minus 3u of t minus 1. And the reason is because we can think of it like the sum of two step responses. So we have u of t, 3u of t, which goes like this, right? This already kind of matches the shape of the response we're looking for. But after 1 second, we want to break it off. We want it to go back down like this, right? So after 1 second, we get another step response and just take away what we put in originally. Does this kind of make sense? Alright, cool. So we can represent the input voltage as 3u of t minus 3u of t minus 1. Okay. And we'll draw the rest of the circuit as well. So we have a, it says a 1 ohm inductor, but I think it's meant to be 1 Henry. 1 farad. And then the last thing was a resistor, I think. 2 ohms. Plus minus VO. Have I missed anything? I have not missed anything. Okay. So the first step here is to find initial conditions. So go back to our 4-step process. Find the initial conditions. So in order to find the initial conditions, what can we do? We can, well, the first thing to notice is that the input is actually a step response, right? So what is the voltage across this, that is supplied by this voltage source before time t equals 0?
0.
It's just 0, right? So our initial conditions are basically that we have a wire here, and then this one goes to a wire, and then this one goes to a open circuit, and we just have a resistor here. So there are two things that we want. We want to know what is the current going through our inductor, and we want to know what is the voltage across our capacitor. Okay, what's the answer, guys? There's no sources.
0.
It's just 0 for everything. This is no initial conditions. Now, this does technically mean that you could use Fourier, but I'm going to do it using Laplace. So let me just write down the initial conditions. The initial current is 0, and the initial voltage is also 0. Okay, this makes it really easy for us, because we don't have to do any of that like independent source magic from before. We can just do regular analysis. So we found the initial conditions, quite simple. We now have to convert our circuit to S domain. Cool. So what we see here is that our circuit has two step responses. Now step responses, when you have u of t, one of the pairs says that u of t transforms to 1 on S. However, we also have a time shift here. So if you recall time shift, that was that f of t minus a times u of t minus a transforms to e to the negative at times f of s. So in this case, our a is just 1 second, and our function f of t is just another step response. So, and the transform of step response is 1 on s. So in total, this 3 u of t minus 1 turns into, using the Laplace transform, it turns into 3 times e to the negative t on s, just like that. So let's actually, with that information, oh, and by the way, this 3 u of t becomes a 3 on s, I should say. So with that information, let's write out what this circuit looks like in the S domain. So our source becomes 3 on S minus 3e to the negative t on s. So it's the same as 3 on s times 1 minus e to the negative t. Oh, question?
Let me know if I'm wrong, but is the voltage source, isn't it meant to be 3ut minus 3ut minus 1? Instead of plus 1?
That's correct.
Because it's shifted.
That is correct. Did I write plus
Would that
1?
affect our Laplace?
It would.
Because it's negative a.
So what's the question? Sorry. So like.
I'm just thinking, wouldn't it be e to the t, not e to the negative t?
I see what you mean. So
the formula is t minus a, obviously, not t plus a, so it should just be 1 anyway.
yeah, so yeah, exactly. So if you think of a equals 1, then this thing becomes.
I see.
Yeah. It's okay. It's just like kind of confusing.
Thank you.
All good. So let's now convert the rest of the elements into the S domain. So this 1 Henry inductor just becomes, well, what's the formula for inductors? It's SL. In this case, L is 1 Henry. So it just becomes S. And similarly, for capacitors, they become 1 on SC. In this case, we have 1 farad, so it's just 1 on S again. And our resistor we can treat as just 2 ohms. Cool. So let me just erase this stuff. And notice I didn't do any of that stuff with the independent sources because this time we have 0 initial conditions. Okay, so we've converted our circuit to S domain. We now want to perform circuit analysis on this circuit to find the output voltage. Like that. So for this one, we can also do KCL on this node. So this node, the voltage here is V0. The voltage here, what is the voltage here? It's going to be 3 on S times 1 minus e to the negative t. So the current going through this inductor, I'll call it IL, is going to be, well, we can figure it out using Ohm's law, but let's actually write out the entire KCL using the currents first. So we have that IL is equal to the current through the capacitor plus the current through the resistor, because the inductor current is entering, but these two are leaving. So we have IL is equal to IC plus IR. Okay? Now IL is going to be the difference across the difference of, like, the voltage difference across this, which is going to be this one minus this one. So we get 3 on S times 1 minus e to the negative t minus the output voltage divided by S. And then this is equal to IC, which will be the output voltage on 1 on S, right? Which is turned into S times V naught. And on top of that, we add the output voltage divided by the 2 ohm resistor. Okay. What I'll do next is get rid of this fraction. I don't like fractions. So we multiply both sides of the equation by S. And I'll also multiply both sides of the equation by 2. So this becomes a 6, this is a 2, and we have 2s squared V out plus SV out. Okay, now I want to solve for the output voltage, so let's just do that. And we get this expression. And then we can get rid of that and move it to the other side. Okay, so we have this expression now. And I'll actually move this S down to the bottom as well. So now it looks like this. Okay, cool. So with this, we have an expression for the voltage in the S domain. Hold on, this should be an S. It's not T. Oops. Sorry about that. So that's an S, not a T, because it's in the S domain. So we have an expression now. Let me look at my notes. Okay, yeah, that's fine. Okay. So we have this expression, we want to do partial fraction decomposition so that we can use the Laplace pairs to transform this into the time domain. Now, the thing that really icks me about this is this part here. Okay? This is really yucky. I don't like it. So what I'm going to do is I'm going to ignore that for now. I'm going to completely ignore it. I'm going to write the equation like this. So I'll basically factor it out. And this becomes 1 on S times 2S squared plus S plus 2. Right? You see that?
You wrote e to the minus t again.
Oh, again, thank you. Yes. Okay, so we now want to decompose this using partial fraction decomposition. I'm going to erase this stuff. We can decompose this, and then we can expand it out and then perform the inverse Laplace. So we can write that as. Okay, actually, before I do anything, I'm going to check. Can I factorize this? How do we check whether we can factorize the quadratic? Well, we check the discriminant again, and it's going to be equal to 1 minus 4 times A times C. And then this is going to be equal to negative 15. So clearly we cannot, this is an irreducible, this part of the equation is irreducible. So we need some A and some B such that, we need some A and B such that we get this. So we need to decompose it. Question?
I remember in one of the labs I tried to do partial fraction decomposition with a non-monic on the bottom, and it just ended up wrong.
Yeah.
So should we always just make it monic on the bottom?
Yeah, exactly. That was going to be the next step. So I think it's very safe when you have a factor of 2 or something, like something not equal to 1. We usually want to divide. We want to get rid of this. So what we can do is we can multiply the top and the bottom by 1/2. So this and this b, we don't care about it, it's just a constant. We can choose it. So this becomes s squared plus s on 2 plus 1. And we'll perform partial fraction decomposition on this. And we can do the same thing here. In this case, we actually do need to care about the 1/2. So we'll move the 1/2 to the outside. And it becomes that. Did that make sense, what I just did? Yes, question? Oh, thank you, yes. So the other thing is, this is a quadratic, meaning that we need a bs plus c on the top. So, what's the explanation for this? I think we just have to.
Well, it's your powers. When you break it down and you do your, you want to make sure that you're accounting for all the multitudes of s
Right.
that are possible, because we know that we can't factor out a constant. So the next highest is a power of x, rather than s squared.
Okay. So for that reason, we have to do this decomposition. Now, one way to do this is algebraic. But what I'll do is a combination of algebraic and residue method. So the residue method, remember, we take our factors and then we substitute in the roots to the rest of the equation. So we can't really do that with this, but we can do it with this s. So we can ignore the s by itself and just sub in s equals 0 to the rest of the equation. And we see that these terms cancel out and we just get 1. So that's our a, which is 1. Now to find the rest of the equation, what we need to do is we need to do a bit of algebra. So I'll leave this up, I need that. We'll do a bit of algebra. So we know that this thing is equal to what we have here. It's equal to 1 on s times s squared plus s on 2 plus 1. So what we can do is we can multiply this out such that this right hand side is equal to 1. So what happens is we get s squared plus s on 2 plus 1 plus s times bs plus c is equal to 1. We now expand and we get bs squared plus cs is equal to 1, and we group the terms. So we have s squared times b plus 1 plus s times c plus 1 on 2 plus 1 equals 1. And implicitly what we actually have here is we have 0 times s squared plus 0 times s plus 1. So you can see the 1's already match up. That's fine. Now we need the s term to also match up. So we can solve this equation. Equals 1. Hence we have that c equals negative 1/2. Similarly, we need the coefficients of s squared to match up. So we get that b plus 1 is equal to 0 as well. Which means that in the end, b equals negative 1. Cool. So we now have the two factors, two coefficients, b and c. Question?
You mean c is equal to a half, positive half?
Yes, positive 1/2.
What is it c plus a half is 0, 1?
That's also true. So it is negative 1/2.
No,
Okay.
no.
Okay, that was very lucky. Alright. So we have negative 1/2 and negative 1. So we can erase all of this. That's fine. And let's actually just replace the bs plus c with minus s plus 1/2, like this. And if you wanted to, during exam, what I would do is I would actually try and bring these together and check that it does match up with what I expect. That's one good way to check. So what we can do now is try and think about our pairs. So this is where we actually begin to think about which pairs we're going to use. So you'll notice that all of this is still multiplied out by 3 times 1 minus e to the negative s. And this is all equal to the output voltage. So it turns out that when we multiply out this constant term with these two, this just that's just like as normal, right? We can do our pairs and figure it out. But when we multiply this out, this corresponds to a time shift. So if we think about the time shift property, is that f of t minus a times u of t minus a corresponds, if you take the Laplace transform, to e to the negative s times f of s. Yeah. Is that correct? I think so. Okay. So basically what we can do is we can try and figure out some Laplace pairs which match up to these, and then we can expand it out and we can find the output voltage, the output waveform. So the best thing to do here probably is notice that this matches up with our sine and cosine pairs again. So if we go back, you can see that it matches up slightly, kind of with this. It's irreducible. We've already determined that, so we have to do sine and cosine to this. So let's actually turn this into something that we can work with. What I'll do is I'll make it match up with this one again by completing the square. So on the denominator we have s plus 1 on 4 squared And we also have a negative 1 on 4 term. And then plus 1, which is the same as plus 4 on 4. Hence we have plus 3 on 4. But just as in the previous question, we're going to take the square root and then square it. So we get root 3 on 2 all squared like this, which is similar to the previous question. And then we need this a term off the top. We need s plus a. So what we can do is we can just force an a term. So a here is 1/4. So we do s plus 1/4 plus 1/4. So you'll notice that the 1/4s match up and they add up to give a 1/2. Cool. The next step is, so we have the rest of this still, so we can't ignore this. That's still important. But we also have, like, what we can do is we can actually take out this into a new fraction. So let's erase that. And we do plus 1 on 4 times s plus 1 on 4 all squared plus root 3 on 2 all squared, like this. Now this one no longer has an s term, so we need to make it match up with something else. In this case we can use the sign pair. And this ends up being times omega on omega. So we can just do this, where omega is root 3 on 2. So I haven't changed the equation at all, it's just multiplying by 1. So we can move the constant out to the front. So it's going to be 1 on 4 omega, where omega is this, so it's 4 root 3 on 2, which is the same as 2 root 2. Right? And then omega is just root 3 on 2. Okay. Cool.
2 root 3.
2 root 3, thank you. Lots of mistakes here. 2 root 3. Okay. Now on the outside, this is multiplied by the 3, and it's also multiplied by the 1 minus e to the negative s. So what we do is, this is pretty yucky. We're going to have to expand it, and we'll get 6 terms in total. So what I'll do is, am I short on time?
No.
Okay, question?
I was just wondering why it's got to be plus, because it's minus outside the front of the first one. Does it have to be a
Oh,
bracket?
good catch, good catch. This is meant to be minus, yeah. Okay, nice. So what I'll do is I'll expand this entire thing, and then we'll take the inverse Laplace. So it's a bit involved, but it's okay. Okay. So we have this expression so far. We want to expand it with this. Well, this one term will expand to give the same thing. So I'm just going to leave it like this. We've already done half of it. But the rest, the minus e to the negative s, we have to expand that out. So I'll just multiply it out like this. Okay. So all I've done is expand the brackets, and I have these two pairs of equations, of expressions. So what I want to do is, I want to do the transform, the inverse Laplace of this. Was it 3 minus s e to the s, negative s, or? No, I think this was like that, yeah. Okay, so the first term, so let's actually erase the original equation, the what do you call this, circuit, because we don't need it anymore. Oh, and I forgot to mention, we have done the analysis. We are now doing the inverse. So we erase the entire circuit, just so I have some more room. And let's start by taking the inverse Laplace of this term. So using our pairs, we can see, well, if we go back to the pairs, oh, I think the pairs are up actually. This corresponds to just u of t. So that's our first term. Get rid of that. We now have this. We now have this term. This one is one of the sine cosine ones. We see that A is equal to 1 on 4, and omega is root 3 on 2. Which matches up with this. E to the negative at cosine omega t. So it's minus 3 times e to the negative 1 on 40 times cosine root 3 on 2 t. Similarly, this is the term that matches up with sine. So this becomes minus e to the negative 1 on 4t sine root 3 on 2t. Okay, so that's our first 3 terms done. We now have to do the second set of terms. The second set of terms. So we can expand it out. The first term is going to be negative 3 e to the negative s on s. How do we take the inverse Laplace of this? Well, if we look at our pairs, if we go back a bit, we have to use one of the properties. We have to use specifically the time shift property. So notice that the time shift property says that if we shift it in time, we have to take the same like transformed function and multiply it by e to the negative s. So what we have here is some function times some function times e to the negative s. So we can take the inverse Laplace of this and then shift that using negative 1 in the time domain. So the inverse Laplace of this is actually the same as this, So we take that, and this is all minus, by the way, so let's do that, minus. And we take it and we shift it in the time domain by 1. Is that okay? Make sense? In the same way, we have multiplied this e to the negative s term out with these terms as well. So we can just take what we already have and time shift it by 1. So it's the same thing, but it's time shifted. Easy. And this one as well. Okay. Any questions? That's the question answered. So it was quite involved, but we got there in the end. And we have. Okay, and then we'll move on to poles and zeros. We'll do another. There's another Laplace question that we can do, and then the next part of it is poles and zeros. So, how are we doing on time? Should I just? Okay, I'll just do the entire question. All right. So, let's have a look at this question, and then we'll get on to poles and zeros after that. Well, as part of this question, rather. Alright. So I'll still leave this up because we need this. The question has this circuit. We have some input voltage 10e to the negative 4t times ut. Cool. What do we have? Is that 1 on 3?
1 on 3 farads.
1 on 3 farads. What's this one?
1 Henry.
1 Henry.
And 2.5 ohms.
This one? And what was here?
2 iron.
Okay, cool. Okay. What we want to do is we want to find this output voltage in the time domain. So again, the first thing that we have to do is look at our initial conditions. However, in this question, they actually tell us that the initial conditions are all 0, which makes me really happy. I don't have to do any initial conditions. So we have that the initial current is equal to 0 amps, and the initial voltage is also equal to 0 amps, 0 volts rather. So then we can skip straight to converting the circuit into S domain. So I might actually just leave it here and do it. First we have to convert this 10e to the negative 4t times u of t. So let's go back to our pairs. And we'll see that it's 10 on s plus 4 using this pair right here. E to the negative at transforms to 1 on s plus a. So we can use this pair and transform this into ten on s plus 4. Okay. Now, using Ohm's law for capacitors, we have that this one turns into 1 on SC. In this case, C is 1/3, so this is 3 on 4. 3 on S rather, sorry. And our 1 Henry inductor becomes just S. Cool. What we can do now is, well, there's a number of ways to do it, but the way that I'm most comfortable with is nodal analysis. We can take a look at the currents entering this node and leaving this node. So let me just label these currents. I'll call this IC for I capacitor and IL for I inductor. And we can just perform nodal. So first of all, let's write out the equation. IC equals IC plus 2I. And I should mention that this is actually the same, this is actually just I in the question. So we have that I plus 2I is equal to IL. Okay? This is the same as 3I equals IL. And I should write this as capital because it's in S domain. Okay. So 3I equals IL. What is IL? That's just the current going down this branch. Which means that we can just represent that as the output voltage divided by 2.5. Okay. The other thing we need is an equation for I. So to find I, we take the voltage in these two nodes. This one I'll label V1, and this one we have from the voltage source. So we have that I equals 10 on S plus 4 minus this V1 divided by 3 on S. Okay. We have to find an expression for V1. So what we do is we then take the voltage across here, V1 minus V out divided by S, and we know that this is equal to IL. Okay. And IL is the same thing as V out on 2.5. Cool? So what we do is multiply it out, and we'll move all of the V outs to the same side. And we factor out the V out. And we have this expression for V1. So let's actually sub it in. We have that I equals to 10 on S plus 4 minus the output voltage times 1 plus S on 2.5. Like this, divided by 3 on S. So it's a bit ugly, but we have to work with it. So get rid of this. Now this is an I equals something. So what we can do is we can multiply both sides of the equation by 3. And cancel these out. And since we've multiplied both sides by 3, we know that this is all equal to V out on 2.5. So what we can do is, this S on the bottom, we can move this to the top, and then we can divide it here. So our expression is becoming a bit nicer to work with. And we can get rid of the I as well, because we don't care anymore. So again, just like before, we have to solve for the output voltage. So let's just do that here. We have the 10 on S plus 4 equals V out times 1 plus S on 2.5 plus 1 on 2.5 S. And we can just turn this into one fraction. (2.5s) plus s squared plus 1 on 2.5s. So almost there. And we find finally we solve for the output voltage. So that we have V out equals 10 on S plus 4 times 2.5s multiplied by S squared plus 2.5s plus 1, like so. Okay. Now we want to, so what I'll do is I'll multiply and divide both sides of the equation by, actually I will not do that, I'll just leave it like this. So the top becomes 25s. So what I'll do is I'll take out a factor of a half, and then we'll multiply this inside by 2. Okay, so this is 2s squared plus 5s plus 2. Well, this one we can just turn into 2s squared plus 4s plus s plus 2, which is the same as 2s times s plus 2 plus s plus 2. So it's just factoring out. We have this expression. So we'll erase the rest. So almost there. And we have this. And what we do is we divide the inside of this by 2, get rid of that, and we get plus 0.5. Which, if we go to the question, if we go to the question, is exactly what they're looking for. Okay. Any questions so far? Okay. So the next parts are significantly easier because we've already done most of the work. Wait, actually, did I even answer the question? Yeah, I did answer the question. Okay, show that the output voltage is in the S domain. Yeah. So we now have to demonstrate that the transfer function is that. So maybe I'll leave the equation up. We have that h of s equals V out of s divided by the source s, right? We've already found V out of s, and that goes on the top. And V source of s is actually just this. We've already found it. So we can just sub these in directly and we can answer the question. So s plus 4, s plus 0.5 times s plus 2. This is our v out of s, and then we divide it by v source of s. So we multiply it by s plus 4 on 10, which causes these s plus 4s to cancel out. And hopefully we get the same thing, almost. Oh yeah, same thing. 2.5. Okay. Make sense? Okay. We now have to sketch the poles and zeros of h of s from question 2 on the s-plane, clearly indicating all the points. So, let me write h of s somewhere. I'll just keep it here actually. Is that correct? Yeah, okay. Let me get some more chalk as well. Okay. Sketch the poles and zeros. So, there's two things that we need to know, like what is a pole, what is a zero. So let's actually go back at this point to the previous slide. Zeros are the roots of the numerator of h of s. So we have h of s, we have a function on the top, it's the numerator, and we have a function on the bottom, which is the denominator. So the zeros of the numerator, in other words, this bit, are the zeros of the entire transfer function. So our zeros are s equals 0. That's the only root we have here. Our poles are given by the roots of the denominator. In this case we have s equals negative 0.5 and s equals negative 2. Okay, so let's graph this. We draw an Argand diagram. This is just it's just a complex plane, right? And remember that, so this actually represents s. So remember that s equals sigma plus j omega. So it's like we're graphing s, right? Okay. So we draw the zeros at s equals 0. So we just draw a circle here. Circle, I think it's circle, right? I think it's circle. It's a circle, yeah. And then we draw the poles at negative 0.5. Now this is just a real number, negative 0.5. So we just draw it on the real line. And we also draw one at negative 2. Done. And then the question asks us to clearly indicate all points. I've done that. We have to state whether the system is stable or not. And the way that we can check stability is with these two conditions. The first condition is that all of the poles must be on the negative real axis, meaning that they must all be on the left side of the plane. So we can see that the poles, they are on the left side of the plane. So this first condition is checked. The second condition is that the degree of the denominator. Question?
I thought in on the lectures she said to like not consider this the second condition for stability, because like technically even sometimes if that isn't fulfilled it still can be stable, but the course doesn't go into enough detail.
Alright, I think is she referring to maybe like input signals or something?
Yeah, that's probably.
I don't know. Okay, anyway, I actually didn't know about that, but
I believe if your degree of the numerator is greater, then you don't have a. It gets funky with certain frequencies.
I think it means when it's like equal, the degree of the denominator and numerator are the same. It's still stable, but that's because it's bounded, because it's some constant,
right.
I guess.
Anyway, I'm not 100% sure, but it might be worth keeping in mind anyway, just for the context of this course.
Sure.
So we have the second condition, which we can check. We can see that the degree of the numerator in this case is just 1. We just have 2.5s. And the degree of the denominator is s squared, it's 2. So the second condition is fulfilled either way. Yeah, any questions? Okay. That's it for Laplace. We now have... Yes, question?
Does this circuit have a resonant peak?
Does this circuit have a resonant peak? I'm going to be really bad at answering this question. I guess not, right? Probably not, because if you think about it, this will cause kind of like a, well, if we decompose it, we have something like 1 on s plus 0.5 plus 1 on s plus 2. Our response is going to be negative exponential. So I guess it doesn't really have a resonant peak. I believe there's a whole bunch of like deep connections between resonance and poles and zeros and stuff, which I have not looked into yet, but I think it's really interesting. So yeah. Any other questions? Yeah.
Yep.
Cool.
One last topic.
Yes.
Okay, I hope you guys are all still awake, because you've been sitting here for 2.5 hours now. Thank you to our previous presenters. Can we give them another clap? I'll just quickly take you through two-port networks. Let me just get something up here, and then you guys can have a good nap. Okay. Okay. Let me just get this on the screen. Here we go. Oh, it doesn't like me. Okay. If it doesn't like me, it doesn't like me. That's fine. Okay, we'll just do it on the blackboard. Okay, guys. Need your attention just for a little bit. Is any of the good chalk left?
All of the chalk is the good chalk.
All of the good chalk.
I think we've taken all the good chalk in this building.
Pretty good. Okay, this is what we used to have. Black box. You have one wire in, one wire going out. You have a voltage and a current. This is what it used to be, right? Now, this is a circuit. Every circuit we've done previously is basically in this form of some sort, right? Now, I'm going to ask you a question. What happens? So we can represent this circuit with like a resistance and a V-Thevenin usually, right? That gives us the circuit. But I'm going to ask you a question. If I add over here 2 more wires, 2 more things that can change this voltage, the one and this one, this current, what's going to happen? What do we need to do to represent this circuit now? Instead of just resistance, which would just be the ratio between those 2 things, we're going to need another thing. We're going to need more than one other thing. We're actually going to need 4 things. You guys remember this? These is what a 2-port network is. 2 of these things, right? Before, we only had Z and Y. So this is in regular circuits. This is what we had. We had 2 ratios, right? We had the ratio of V divided by I, right? And we had Y, which is the ratio of I divided by V. But now, we need a lot more, because we're going to represent this thing, we're going to need 4 numbers, because we have 2 inputs now, not just one, right? Okay, so maybe this is going to be best done by showing you this. Can you guys all see? Yeah. So, if we have over here, these are our Z parameters. People are used to this. Okay, we've also got a ton of other parameters, which I would show you right now, but my computer's not liking it. Instead, what I'm going to do, well, actually, I can grab it. I can just get it from the slides. Here we go. This is going to make our lives easier. Okay, just over. Where's the list of them? Did I go past it? Oh, here we go. This is exactly what we want. So before we just had one thing, one dependent, one independent. Now we have two dependent, two independent. And when you start doing combinations, you'll realize you have a lot more that you can possibly represent. So I'm going to take you through a couple of questions. All we're saying is the only thing that's changed here is instead of using one ratio to describe the circuit, we now use 4 ratios. Make sense? Okay. Let me get a question up. Okay. Here we go. I'm going to ask about something called T parameters. Can everyone see them over on the board? T, transmission. The reason they're called transmission is because when we represent them, like this, we have the T parameters. So let's say this is circuit A, circuit B, and we want to call this whole thing circuit C. C is going to be equal to A times B, just matrix multiplication, because these are just represented by matrices. So yeah, I'm going to draw a circuit over here. It is R1, R2, R3. R2, R3, and we're going to be asked to find the transmission parameters. Okay, here we go. Now, let me make this a bit cleaner. Okay. Can anybody please read off what A, B, C, and D are off this? Does anybody know how to calculate them if we have this form?
So do we set like I2 to 0?
Yeah.
And then solve for each of the ratios?
Exactly. So let's write it out. Our A parameter here is going to be equal to, I'm just going to divide both sides by V2, right? We're going to say, sorry, that was the wrong one. But yeah, V2. So V1 on V2. And as Anuka said, I2 is 0. Okay, and we're going to do it for the rest. We can write them all out. Does somebody want to give me what B, C, and D will be?
V1 on I2.
V1
On I2.
V1 on I2.
On negative I2.
No, that's right. That's right. Yeah. V1 on negative I2. Where what's going to be equal to 0 there?
V2.
That's correct. Okay, can somebody give me C?
I1 on V2.
Yep.
Where I2 is 0.
And the last one? Just shout it out.
I1 on negative I2. V2 is equal to 0.
Okay. Sorry, that took us a while to get there. will all be worth it. Okay, what we're going to do with this one, probably should put this a bit further up, but we'll manage. We are just going to solve these. See, it just turns into a normal circuit analysis problem, right? That's V1, that's V2. These are always going to be where they are, and I1 is always heading into here, and I2 is always heading into here. Okay, can any, what I'm actually going to do, the first thing I see here is I'm wondering, how am I going to solve this, right? Well, I could, there's one of two analyses I can usually use for something like this. Yeah?
Can you push the mood up a bit?
I can put the water.
Not too high.
Can everyone see?
Yeah, it's a bit.
Okay. I'm going to use, I think I'm going to use mesh analysis here because I've got two meshes and I've got 3 nodes, so it's going to be easy to do mesh here. Now I'm going to do this. I1, I2, already given very nicely. Let's write on plus, minus, plus, minus, plus, minus. Okay, let's do it. First equation, minus V1 plus R1 I1 plus R2 I1 plus I2. There's actually 2 ways of doing this. So in your thing where we say V1 or V2 is equal to 0, what you can do is you can do it directly in the circuit, right? Or you can solve the circuit and then sub it in. I prefer the second method, where you solve the circuit just generically, then you sub it in. It means that you don't have to do more calculations, and it's kind of nice. It cancels out kind of satisfyingly. Yep, so this is equal to 0. So we can just say V1 is equal to this. And next one, V2 is equal to I2 R3 plus R2 I2 plus I1 plus I2. So same stuff. Let's solve these. So you usually solve them in pairs. You might think A and B go together, but it's very easy if you solve these 2 and these 2 together because you're setting the same constant equal to 0. Let's sub in, let's do A and C, let's sub in I2 equals 0. So we sub in I2 equals 0, that goes to 0, right? We just get I1, R1 plus I2. And then V2 is equal to, we say I2 is equal to 0 again. And we get, we just get I1 R2. So if we want to solve this, it's just your algebra manipulation skills. Here, this one's actually quite straightforward. Divide these, and we'll get A. Everyone can see why I'm dividing these. The R1s cancel out, and you'll get R1 plus R2 on R2. There we go. Next, C. We want to find I1 over V2, right? Now, what do we have here? We have V1 over V2. This one's V1 over V2. And we want to find I1 over V2, right? So what we can do is we can sub this in, right? I1, R1, so into just this thing. Because we want, no, my bad. It is actually easier than that. It's just I1 over V2. There we go. My bad. I1 is equal to, I1 on V2 is equal to 1 on R2. Even easier. C. Okay, so we've got A, we've got C, and then let's just do our analysis again. Instead of subbing in I2 equals 0, what are we subbing in? Yeah, V2.
Also,
yeah, V2 is equal to 0. And this one is a bit less nice. The other one cancelled out quite nicely. Just in terms of a method, what the actual method is draw this stuff in, see the best term of analysis, right? realize what ratios you have to find, and then just do the circuit analysis to find the ratios. That's what I've been doing. Probably should have made that more explicit at the start. Okay, V2, right, is equal to 0. We can probably get rid of a lot of the stuff that we've already done. So we need to see. We need is C and A, which we've got. Let's get B and D. V2 is equal to 0. That means we can write I1 and I2 together. So let's do that. So minus I2 R3. Well, let's group like terms actually. I2 R2 plus R3. We're just doing that, plus I1 R2 is equal to 0. And over here, we do not have V2, so it's all nice and dandy. What are we going to find first? V1 on negative I2. So let's find V1 on I2. We just need to sub in. I'm going to group like terms because it's going to help us here too. Let's do I1 plus R2. And then I2 plus I2 R2. Okay, and what we're going to do with that is we are going to sub in this relation we've got. So I'm just going to write I1 is equal to, so one of the equations we need anyway is D. We've actually got it quite nicely over here. So I1 over minus I2. Can everyone, that's a bit small, but that'll be fine. I1 on minus I2, right, is going to be equal to R2, right? Because I'm going to negative that for both sides. Divide by that negative I2. I'm actually going to write it out instead. I1 R2 is minus I2, R2 plus R3, and then I1 over minus I2 equals R2 plus R3 over R2. Hope I'm not putting you to sleep yet. That is exactly what we wanted for D. And C, B, V1 minus I2, what we can do is we have this over here, we just have to sub in we don't want I1 in this term, so we just have to sub in our value for I1, which is, we can write over here, I1 is equal to, from this, negative I2 R2 plus R3 over R2, and then we can just sub it into this equation, group like terms, and we'll get what we want, which is V1 on I2. Yeah, that will work. Over here. So this is a lot of really long circuit analysis. That's basically what this is. You've done mesh, you've done nodal before. You just need to know how to get into the two-port network, what you're trying to find, and then you know everything. It's just a small addition just to make questions a little harder. But it's basically free if you know what you're doing. Here we go. B is equal to, let me do this. V1, so we sub in the I1 over, who we got over there, okay. Make your working neater than mine, and you'll have an easier life. Okay, negative R2 plus R3 on R2, and we also have, from this term, R1 plus R2. Plus, you can't see that, can you? Okay, I'm just going to write out what C is. C is, because you can do all the maths, this is just wasting your time at this point. C is, B is R1 plus R3. You see what you do here though. You group the like terms from this equation and divide and find it. So C equals R1 plus R3 plus R1, R3 and R2. I'm going to clean up this board. Does anybody have any questions? I mean, not about the annoying algebra, but about how two-port networks work or how you'd approach a problem or any problems that you want me to solve for two-port? I've got another one, but it is a little nicer. Do we think one more question or? Yeah? Let's, what?
May as well say it, we'll do that.
Yeah? Well, I hope you guys aren't getting too hungry because this one doesn't take.
Is it a pi network?
This will actually be a pi network. And it's H params, which is fun. It is like this. P1. It's got an interesting feature, which is a dependent source.
So it's not reciprocal.
It's not a big one.
It's not, well, with some of them, if they're reciprocal, we can just,
Yeah. No, I know what you mean.
like,
No, not with this one because it's dependent, which is kind of annoying. Another thing to mention. That's actually a good point. Another thing to mention about this in general. Okay, I'm just going to come up with an example. If I have Z, because the ratios are all the same. Once you've found one ratio, you actually don't need any more information about the circuit. Any of these ratios represents everything about the circuit that you need to know, right? So if I have Z, I can turn it into any other type of ratio, right? And it's just some matrix stuff. The most obvious ones are Z and Y are inverses. Just like a lot of it acts, because Z equals V on I, right? And Y equals I on V. This is usually it, right? But that's just in normal, but just like in normal, Z equals Y inverse. So, and you get the same thing between certain things, T and T inverse, H and G. And I don't think they need to memorize this for the exam, do they?
Emma told us not.
Emma told you not? Okay, that's always good.
She didn't tell us not.
No, she didn't. All right, let's go back up. We're going to do our H params. So, yeah, let me finish drawing the circuit because I got distracted. Part I. And we have, this is I believe. And that is it. So I'm actually going to take you more through the way I'm thinking about this. Okay, what do I see? I see two-port network and they ask for H params. So what am I thinking? What's the first thing I'm thinking? Well, I'm thinking of drawing, so they'll just give it to you like this. They actually won't give you the plus and minus sometimes. So the first thing I'm going to do is draw this stuff. They'll usually give it to you. But I'm going to be thinking about this. Okay, I've got to draw this. And I've got to find certain ratios. What are the ratios I need to find? Well, that's going to tell me something. And also, how am I going to solve this circuit, so to say? Like, get every ratio in terms of every ratio. So first, hybrid parameters. V1. What do you say you guys don't need to memorize this?
If it's anything other than impedance, she'll give us the.
What? Oh, lucky guys. But here.
Thanks for my experience there, mate.
Okay, I think that's it. Okay, that's a little far off the board, isn't it? Can you guys see that or no?
I think
just not. Oh, that's annoying. Yeah, wait. Oh, I don't think.
The parameters are just infinite. Actually, no. If you move it down a bit,
Yeah.
move the board down, then it fits.
Must be at an angle or something. Can you see?
Not like you don't need to super far down. It's mainly because the stream is
Definitely more efficient.
There's also people on the right.
Okay. That fits then, right? Are we fitting it now?
Yeah, very much.
Okay, good. I can move it a bit up, so there we go. Okay. What is the first thing I'm thinking about this circuit? Okay. Well, I see this dependent source, which seems a bit annoying. I'm thinking about what analysis technique am I going to use, right? And does any analysis technique jump out to somebody, like straight away?
Is it nodal?
Yeah, 100%. Why did nodal jump out to you?
Because, well, I know for T networks we use mesh, and this one we use nodal.
That's exactly right. That's a good reason. The reason is we've got 2 nodes, including ground, and we've got 3 meshes. And if something's easier or harder, we're going to make our lives easier. Okay, this node is at V1, this one's at V2, and we just need to do our KCL equations at each node. Okay, let's write all our pluses and minuses in, and that should all be good. Okay, here we go. The next thing I'm going to do is, analyze the equations. So let's do node 1. Let's do our KCL. This should be I1. Okay. At node 1, we have I1 coming in, and we have that being equal to this I, right, which is V1 divided by 1, and we also have coming out this one, which is V1 minus V2 on 9. Like I said, I can take you through this, but it's the same as any other analysis technique. You know, you've been doing this since quad 1. Practice always helps, but practice always helps. And then we'll do I2 is going to be equal to, what are we going to have? I2 is equal to this one coming out, 5I, and we figured out I, by the way, is equal to V1 on 1, so it's just equal to V1. So we're going to have this coming in, and these two, this is also going to be coming in, so actually I2 plus V1 minus V2 on 9 is equal to 5 V1. That seems right. And what we're just going to do is, what do we need to write out? So does everyone actually know, this is actually a good thing to know, does everyone know if you have this form, like how to read it off, so what ratios you need to find?
You just do matrix multiplication.
Yeah, that's a good way of doing it. You can read it off straight off the table, but
Match the row with the column or something.
exactly. So if you have first row is going to be this one, and as we move along, this goes with this one, so it's going to be this one and this one make this one. It's just kind of a visual thing you learn. It is best to do matrix multiplication. Okay, V1 is equal to H11, I1. So I'll just write out the ratios. You know how to read them off and sub it in and all that stuff. I'm not going to go through that. So H11 is equal to V1 on I1, where V2 is equal to 0. H12 is going to be equal to, etc., etc. We'll come back to it when we need to come back to it. Okay, we're going to try to figure out H11 and H21 first. These two go together. So H21 is equal to, what is it equal to? It's equal to, it's this one, so it's I1, it's I2 is equal, it's I2 on I1. Where V2 is equal to 0. these go together very nicely. Sub in V2 equals 0. We end up getting I1 plus V1 is equal to V1 plus we minus V2, and V2 is 0, so it's just V1 on 9, which means we can just write this as 10 on 9 over here. And then we also have this one, which gives us that we're going to times everything by 9 to make our lives easier. 9I2 plus V1 minus V2 equals 45 V1, and we end up finding that over here, this is V2, 44 V1, and V2 is 0, so we can get rid of that. 44 V1 is equal to 9 I2. So what can we find from this point? So we can already do V1 on I1, that's equal to 0.9. We can already do I2 on I1, because we can solve for V1 over here. So V1 is equal to 9 on 10 I1. Sub this in, right? Divide by 9. We get I2 is equal to 44 I2 on. That's what we want. No, I2 on I1, I mean. Shouldn't be skipping steps. Bad habit. That's not true. We sub in this thing, 4.4. And don't do what I just did. Remember to put units in. Units are incredibly important here. You will probably lose marks if you don't put in units. Trust me, I know. This is just a ratio of two numbers, so you can leave it as 4.4. And then we just have to do the rest of the stuff. Get rid of this. I'm going to be honest, not the most fun topic in 2134, but you'll be glad you practiced it if you have in an exam, because it's basically marks you can get pretty consistently. Okay, next thing, what are we setting? We are saying H12 is equal to V1 on V2, where I1 equals 0. And we get H22 is I2 on V2, where I1 equals 0. Very nice. Okay, let's just do it, and then I1 equals 0. We can group like terms. 0 is equal to, we get V1, that's 10 on 9 V1, minus V2 on 9. And we can do another one over here. What if we set a 0? We said I1 is 0. This one doesn't save us. We just get, that becomes 46, I think. No, 44 on 9 V1 is equal to plus V2 on 9 is equal to I2. Okay. And what do we need to figure out? We want to figure out V1 on V2. That is given to us at this point. V2 times both sides by 9, we get 10 V1. 10 V1 is equal to V2, and we get V1 on V2 equals 1 on 10. So 1 on 10, which is 0.1. Does it have a unit? It does not have a unit, because it's just the ratio of these two. And H22, I2 on V2. We don't want V1 in here, so we put V1 on V2 equals V1 on 10. V1 equals, V1 equals V2 on 10, and we get 4.4 on 9. V2 plus, we can make it 5.4 on 9. V2 V2 is equal to I2, which means we can solve I2 on V2 is equal to 5.4 on 9, which looks like it has a nice thing, because that's like 6, right? That's like 0.6. And the unit is Siemens. Okay. Any other questions? Anything? Anything throughout the crash course? Okay. I think we're all good. You guys have stayed a long time. I'm surprised you guys are awake. All right. Has everyone taken attendance? Okay. Thank you for coming, guys.
ELSOC?
Also.
Good.
I think I'm on.
Time to pass out.
No, I'll wait for after the exam.
When is your guys' exam? No, not next week. That's
Tomorrow. There's a reason Emma didn't get us tonight. Oh yeah, I can flip this. How many of these did I break? Like 2, 3? I don't think too strong, you think?
Everything with chalk for
Yeah.
really nice Japanese stuff.
Hugger
Oh,
Yeah.
you saw the video on YouTube.